are two very famous theorems in probability theory. One of them I will discuss and prove at the end of this lecture. The other one we'll do in the next lecture. But before that, I need to get through some technicalities. One of them is discussing the function which can generate the moments of any probability distribution. So you give me a probability distribution and I'll show you this function which, if you can differentiate once, twice, thrice, whatever, you'll get the first moment, second moment, third moment, or whatever. Very, very useful. Then we'll take the binomial distribution and other distributions as examples, but the binomial distribution is going to be particularly important because when you take the large n limit of that, you get to a very smooth distribution called the normal distribution. And this is absolutely fundamental in probability theory. We'll show, using some mathematics, how the binomial goes over into the normal distribution. And then this will set the grounds for our next lecture as well, but by itself, this will be an important result. I'm going to begin by defining a function that we will use for generating the moments of a probability distribution. This involves a very useful trick. So, suppose there is a random variable x, we want its expectation value. Well, that expectation value is got by weighting the possible values of x with the probability of x and then integrating over all values of x from -infinity to +infinity. Now, I'm not going to show this because we need this integration sign again and again, and it's understood that this integration is over all possible values of x. Now, we know that if we differentiate tx with respect to t, then the answer is simply x, and of course I can put t equal to 0 at the end of that, and that's trivial. I can similarly write the expectation value of the square of x by weighting the square of the possible values of x, weighted by the probability distribution, and here there is tx squared, which if I differentiate twice, well, the second derivative of t squared is 2, and so I must put a half over here, in which case I will simply get back x squared, p of x dx, and that's this. Obviously, this can be continued to x cubed, to x fourth, and for any n we can write the expectation value of x to the power n as this, and then we need to just have 1 over n factorial, because when we take d by dt n times of t to the n, then we'll get an n factorial which will cancel this. At this point, it is not important that we put t equal to 0 because, after all, the derivative of t to the power n over n factorial is just 1. However, this t equal to 0 will be essential because I'm now going to define the moment generating function of the random variable x as a function of t by integrating e to the power tx weighted by the probability p of x, and the integral, of course, is over all values of x from -infinity to +infinity. Now, if I was to expand this exponential out in its power series, in fact, that's the definition of e to the power tx, well, that's 1 plus tx plus half tx squared plus 1 over n factorial tx to the power n, etc., weighted by p. Now, the reason that I define the moment-generating function in this particular way becomes clear, because if I take the nth derivative of mx and then put t equal to 0, then I will get the nth power of x averaged. So check this out. Suppose I put n equal to 1. Then if I take d by dt of this above over here, well, this gives you 0, this gives you x, and this gives you t. Other terms will give you t squared, t cubed, etc. But when I put t equal to 0, then all these terms will go away, and I will have simply this term over here contributing for the case n equal to 1. And this term will contribute for n equal to 2. This will contribute in general for the nth term. Now you can see why t was put equal to 0. This is for the continuous case, but for the discrete case in which the random variable x takes only discrete values, you can also define the moment-generating function in this way. So instead of integrating over all values of x, you simply sum over all values of x, or in this case, we've called it k. So k will go over all integers. Again, by taking derivatives of this, we will get the nth moment. Let's apply what we've learned to the binomial distribution, which, as you will recall, is given by this probability distribution. So the probability of getting k outcomes, where p is the probability of getting a single outcome, is then given by n choose k times p to the k into 1 minus p to the n minus k. And I'm going to call 1 minus p q because that's shorter. If you want to remember where the binomial distribution came from, so for example, if p is the probability of getting a head, then 1 minus p is the probability of getting a tail. If you throw a coin n times, then the probability of getting k heads in n tosses is then given by this. And as you very well know, the word binomial distribution comes really from the binomial theorem, which says a plus b to the power n is equal to this. And so if you have p over here and 1 minus p over here, that's 1 to the power n. That is why, of course, all the probabilities sum up to 1. Well, now let's calculate the moment-generating function, in which we take e to the power tx or tk, and then we sum over all the possible values that the random variable x can take. So in this case, k will go from 0 all the way up till n. So now I will take e to the tk multiplied by p to the power k and write it in this way. E to the t times p, the whole to the power k, and 1 minus p to the n minus k. But then from the binomial theorem over here, you recognize that this is exactly e to the t times p plus 1 minus p raised to the power n. So with almost no effort, we have calculated the moment-generating function mx of t, and now we can reap the fruits of that. So if you differentiate this function, which we've just calculated with respect to t, and then you put t equal to 0, you'll get the average value of x. And of course, what happens over here is when t is equal to 0, this is 1, this is 1, and this becomes 1, and so you get the average value is equal to just n times p. That's the result we had before, but now it's got in such an easy way. We can get the second moment in this way by differentiating twice, so d2 dt squared of mx, and then once you put t equal to 0, you get this. So in this case, all you need to do is differentiate this, and after the differentiation, put t equal to 0. And you'll get the second moment of x. So obviously this gives you the variance of x, or the square of the standard deviation, which is np into 1 minus p, which we write as npq. As a second example, let's take the Poisson distribution, which is very useful when you want to find the length of queues, when you want to see how often calls come into a call center, or the waiting time for restaurants, and so forth. Now, this can be derived from the binomial distribution as a special limit, and although we've done it before, let me remind you how this is done. So here is the binomial distribution that you just saw, and now let's introduce a parameter lambda, which we shall keep fixed and finite, and we'll let n be large. So p will be equal to lambda divided by n. You'll ask, what is the meaning of lambda? Well, just wait a minute and you'll see that this is related to an average quantity. Now we can write p of k as n choose k as above, and instead of p, write lambda over n. Of course, this is raised to the power k, and here is 1 minus lambda over n to the power n minus k. Now, look at this quantity, n choose k, and write it in a slightly different way. So n factorial is n into n minus 1, and so forth until this term over here, followed by n minus k factorial, but that will cancel this over here, and so we are left with this. Now, if you look at each one of those terms, well, the first one is just n over n, which is 1. The second one is 1 minus 1 over n, and so forth. And this last term over here, when you divide this by n, gives you 1 minus k minus 1 over n. Now, we're holding k fixed and letting n become larger and larger, so this is going to tend to 1. Now let's look at this term over here, 1 minus lambda to the power n, and that is over here, which we will write as 1 minus lambda over n raised to the power n, and this, the same thing, raised to the power minus k. Now, since k is being held finite, n is becoming larger, so this term over here is becoming closer and closer to 1, which means that we are just left with this term, but this term over here is e to the power minus lambda. And so as n tends to infinity, this quantity over here becomes this. And just in case you've forgotten, you can write this as e to the power n log of 1 minus lambda over n. And now since n is large, this is small, so this becomes minus lambda n, so that's e to the minus n lambda over n, which is e to the minus lambda. Anyway, you should have remembered this. This is a very fundamental definition of the exponential as being this when n becomes large. So what we found is that the probability for the Poisson distribution is this. From here, we're going to calculate the moment generating function, which is e to the power tk times p of k. If you put this in here, it's just lambda k over k factorial e to the minus lambda, and take the e to the minus lambda outside. What this is just the exponential, but is the exponential with this argument, lambda e to the power t. And so here we have the moment generating function as a function of t equal to this. Well, first of all, let's put t equal to 0. We get e to the lambda minus lambda, which is 0. And so mx of 0 is 1, as it should be, because you can see that if t is equal to 0, this is 1. So the sum of all the probabilities is 1, and so this is correct. To get the first moment, differentiate this with respect to t. So if you do that, then lambda e to the t comes downstairs over here, put t equal to 0, so that's just lambda. For the second moment, differentiate the result twice, and you get lambda into lambda plus 1. Again, the variance is very easily calculated. That's just this minus this squared, which is lambda. And so the standard deviation is the square root of lambda. The only trick over here was to recognize that you can actually sum this series. It's just how the exponential is defined. Next, let's take the exponential distribution, which by definition is this. P of x for x bigger than or equal to 0 is lambda e to the minus lambda x. In contrast with the earlier cases, this is a continuous distribution, and so we will have to do integrations. When we integrate p of x from 0 to infinity, we'll get 1. The moment generating function is just e to the tx times p of x. Now, this integral couldn't be simpler. Lambda just comes out. Now, this exponential over here is easily integrated. You get this. And now, what if we put in the value x equal to infinity? Well, then we're going to get e to the t minus lambda into some very big number. Is this going to be finite, or is it going to be infinite? If it's infinite, then this is not defined. And so this integral is undefined if lambda is less than or equal to t, and it's equal to just this, lambda over lambda minus t for t less than lambda, because this term over here is 0 in that case, and we'll just get minus 1 times this, which is lambda over lambda minus t. Again, you can see that the normalization holds out, because if we put n equal to 0, that means no differentiation. That means put t equal to 0 over here, you get 1. See, this over here is 0, so we have lambda over lambda, and so that's correct. What about the first derivative of the moment generating function? Well, we get 1 over lambda from that. For the second, we get 2 over lambda squared. And so again, it's trivial to calculate the standard deviation, which is then 1 over lambda. You can continue this to n differentiations, and so the expectation value of the nth power of x is n factorial over lambda to the power n. The next example is the normal or the Gaussian distribution, and I've drawn 2 bell-shaped curves over here. They're called normal curves, or they're called Gaussians, and in one case, so this upper case over here, this is the function e to the minus 2x squared with this factor in front. The area under this curve over here is equal to 1, and that's assured by this factor over here. And this curve, e to the minus x squared over 2 in red, that's more spread out, but again, the area under this is also equal to 1. Here are the expectation values. In both cases, the expectation value of x is 0, here and here, but here the expectation value of x squared is larger. That's because this red curve extends further out. X squared gets more strength, more support from the probability distribution, and so the average value of x squared will be 1 over here, and it'll be much smaller, 1/4 in the case of this purple distribution. Now, in general, p of x is this thing over here. This is a formula that you should commit to memory because it's very important in probability theory. This is the Gaussian or the normal distribution. So this is 1 over square root of 2 pi sigma squared times this exponential here. You can see that when x is equal to mu, then this is over here 0. So this is e to the 0, which is 1. And so the Gaussian takes its maximum value, which is this thing, 1 over square root 2 pi sigma squared. And so this point over here, you can see is square root of 2 over pi. This point over here is 1 over square root of 2 pi. You know from our earlier discussions that the probability that x is between any two values, a and b, is the integral of p from a to b. So a could be 1, b could be 2. The probability that x takes values between 1 and 2 will therefore be integral 1 to 2 p of x dx. Obviously, this probability distribution is normalized. In fact, I would encourage you to see how this integral is done when you take p of x from minus infinity to plus infinity. It's actually a very simple calculation. I won't do that, but you should know how this value of 1 is derived. Again, since we don't have time to do these Gaussian integrations, I'll simply state that the average value of x is mu. The average value of x squared, which is got by taking x squared and weighting it with p of x, that's mu squared plus sigma squared. And so obviously the variance is this minus this squared, which is sigma squared. Now we can get the moment generating function by taking e to the tx, multiplying it by p, doing the integral. The way you will do the integral is this e to the tx times this thing over here, but you can then simply complete the squares in the numerator, and after you do the integral, you find that this is e to the power mu t times this. So this over here is the generating function for the Gaussian distribution or the normal distribution. Now obviously if I put t equal to 0, then this over here becomes 1, and so does this become 1, and so this over here is correct. The normalization is correct. What about taking the first derivative of this? Well, if you take the first derivative, then this over here will give you mu e to the power mu t, and then you'll have to differentiate this. But when you differentiate this and you put t equal to 0, then this will give no contribution. So the average value of x will be simply mu, the same mu that is over here. And so indeed, the average value, you can see that over here. Here mu is equal to 0 for this distribution and for this distribution. However, in general, this Gaussian will be displaced to the right or to the left by an amount mu. Now here's something that's useful to know. Suppose I ask what is the probability that x lies between mu plus 1 standard deviation and mu minus 1 standard deviation. Well, then I have to integrate from here to here. This integral can be done only when this limit here is minus infinity and this over here is plus infinity. If this is finite and this is finite, then you cannot do this integral analytically. You must do it numerically, and the numerical value turns out to be 0.68. If you put 2 sigma over here, then the probability that x lies between this and this, that is to say within 2 standard deviations, becomes larger. It is 0.95 or 95%. And it becomes still closer to 1 as you go to 3 standard deviations. So there's 99% chance that x will be found having values between this and this. In fact, this is easiest to see with this graph over here. So if we are here at the middle at x equal to mu and look within 1 standard deviation, there's a 68% chance that x will lie between here and here. There's a 95.45% chance that x will lie between here and here, and more than 99% chance that x will lie in this region from here to here. Again, I repeat that this comes from numerical integration. You can't do this by hand, you need a computer. When we talked about the binomial distribution earlier, we saw that it had discrete values with steps like this over here, and this was symmetrical. Now imagine that you were to decrease the size of these steps. Then it almost seems obvious that there'll be a curve that will look very much like a Gaussian that will go through the edges of the binomial distribution. But can we make this quantitative? In other words, can we relate the binomial distribution and the normal distribution in a proper mathematical way? I will show that indeed this is possible. In other words, that the binomial discrete distribution, which is over here, and the continuous normal or Gaussian distribution, which is over here, are very close to each other, but they can't be close everywhere. They can't be close at the edges. You see that over here, the last step ends with a 0, whereas the continuous normal distribution extends out to infinity, both over here and over here. So obviously, if the normal and the binomial distribution are to be the same, they must be so pretty much in this region over here and not outside. So that means for the discrete case, we shall assume that n is large, p is fixed, we should be interested only in values close to the average. So delta, which is x minus np, will be assumed to be a small quantity. And so we're looking at values of x over here, which are close to the average value np. Since delta is small, therefore we will assume that higher powers of delta can be ignored. But now let's make this quantitative. This proof will take a little bit of time, but it should be helpful in revising some basic concepts about exponentials. So, as ever, we start with the binomial distribution, which is this. And now I'm going to use Stirling's approximation for n factorial. As n becomes large, n factorial is approximately equal to square root of 2 pi n times n over e raised to the nth power. Now we can put in n factorial directly from here in the numerator. Then x factorial will be exactly the same with n replaced by x everywhere. So x to the power x. And then n minus x with n minus x raised to the power n minus x. So of course, this 2 pi will cancel with this 2 pi. The e's over here have already gone, they've cancelled out. And so the square root factor becomes just this, n over 2 pi x into n minus x. Now I've taken this n to the power n, put it in here, p to the x is here, q to the n minus x is here. The denominator now becomes x to the x, which comes here, and this comes here. At this point, I'm going to put x equal to np plus delta. So then this denominator becomes n over 2 pi np plus delta. So this comes from this. And n minus x is almost the same, except it's got n into 1 minus p. So that's q. So this n minus x becomes nq minus delta. So now let's look at this numerator over here, which becomes np to the x, nq to the n minus x, and the same thing below. If you look at n to the x, n to the n minus x, well, that's just n to the n, and similarly with the other powers, so you can check that this is correct. What we are interested in is the large n limit. So, as n becomes large, you can see that this n and this n will dominate because delta can be neglected in comparison to this. And so this becomes 1 over square root of 2 pi npq. That's the outside factor. Now this np over x, which was to the power x, I'm going to write as x over np to the minus x. And similarly over here. So I've got negative powers here. Which means that p of x has now taken this form. I'm doing this in stages. And so this factor here becomes 1 plus delta over np. This factor here becomes 1 minus delta over nq. And at this point, I want to remind you that if I have any number to the power c, or rather minus c, it is the same as e to the minus c log b. So just take the log of this. If you take the log of this, this is minus c log b. Take the log of this, that's also minus c log b. And so this is obviously true. I also want to remind you that if I have log of 1 plus something small, then the Taylor expansion gives you epsilon minus half epsilon squared plus 1/3 epsilon cubed, etc., but we don't need those higher terms. So this is just good enough. Let's now use what's above in red. I'll put this in here. So this 1 plus delta over np to the minus x is e to the minus x log of this thing over here. And this is e to the minus n minus x log of this 1 minus delta over nq. So now we will approximate the log in this way and hence get e to the minus x. So the first term over here is delta over np. Second term is the square divided by 2. Similarly over here, it's n minus x. Well, here's the first term, which is minus delta over nq, and then minus half of the square of this. You see over here that the term of order delta cancels. See, this and this cancel amongst themselves because q is equal to 1 minus p. Just work this out. You'll see that the only surviving term is that of delta squared. So it's e to the minus delta squared over 2npq. But you're recognizing npq as sigma squared, the square of the standard deviation. So you can see over here that p of x will decrease rapidly with delta squared. So let's put delta equal to x minus np, and we get p of x is equal to this. Now this is a continuous probability distribution, and so if you ask what is the probability that x lies between x1 and x2, well, then you will integrate that from x1 to x2. Now, because there's a lot of writing over here, we'd like to make this over here simpler. And so let's define a new variable. We'll call that z, which is the deviation from the average, x minus np. but it's divided by square root of npq. Why square root? Because when you square this, then you're going to get this thing over here with a factor of half, and so we are done. The probability that z lies between the values z1 and z2 is just this, e to the minus x squared over 2 dx, with x going from z1 to z2. Of course, this and this are completely equivalent. It's just that defining this new variable is helpful. And of course, you recognize that this square root of npq is nothing but the standard deviation for a binomial distribution. We now want to ask how good our approximation is, because we have used Stirling's approximation and made other approximations along the way. As a typical parameter, we'll take p to be 2/3, q as 1/3. Mu, which is the average, will be n times p, and the standard deviation will be square root of npq as derived earlier. What we want to do is to compare the binomial distribution, the discrete distribution, with the continuous normal or Gaussian distribution that we derived as an approximation to it. So let's take at the beginning n equal to 9. In that case, mu will be 9 into 2/3, which is 6, and sigma will be 9 into 2/3 into 1/3, which is square root of 2. Let's first look at the continuous case, which is over here. If we do the integral of p of x between this limit and that limit, well, that is 0.8664. Now I've taken 1.5 standard deviations here and 1.5 standard deviations here. Now for the discrete case, of course, square root 2 is not an integer. The closest integer will be 4 at the bottom and 8 at the top. The average value of x is 6, and so we're taking a little bit above and a little bit below. The probability of finding x between 4 and 8 is 93%. That's approximately equal to what we have in the continuous case, but the approximation is not very good. This is more like 87%. However, if we go to 90, so in that case the average value of x is 60, and then 1.5 deviations approximately above and 1.5 standard deviations below, well, this sums up to 0.88, 88%. This is obviously better than 93%, but it's going to become still better when we go to 900. The average value of x will be 600, and then again 1.5 standard deviations above, 1.5 standard deviations below. If you ask what is the probability that x will be between here and here, that's 87%. Again, that's not exactly what's over here, but rounding off is 87% as well. However, if we go to 9,000, then we see that the approximation has become substantially better. It's now 86.8%, whereas over here it is 86.6%. What we are clearly seeing is that the difference between the continuous case and the discrete case is becoming smaller and smaller as n becomes larger and larger. The result that we've obtained can be looked at in a slightly different way. So, let's define n independent, identical random variables, xi, where I goes from 1 up till n. Let this random variable x take the value 1 if the ith toss is H, is a head, and 0 if that toss gives you a tail. Here P is the probability of getting a head. It can be equal to a half, as is most usual. However, it can be different from half if it's a bias coin, like this one, where P is 2/3 and 1 minus P is 1/3. Let's define Sn to be the sum of these n random variables. I is 1 through n. So just sum up x1, x2, all the way up till xn, call it Sn. Each of these random variables, x, takes the value 1 with probability p and takes the value 0 with probability 1 minus p. These add up to p. By the rules for calculating expectation values, the square of xi will be, again, 1 squared times p plus 0 squared times 1 minus p, and that too is p itself. So obviously, the average of Sn divided by n, we're going to call that mu x. That's n of these p's, and then you divide by n, and so that's p, and that's the average value of n trials. So if you flip a coin n times, then the mean value of Sn will be simply p itself. The standard deviation, or rather the standard deviation squared, is simply this thing squared minus the average of xi squared, and that's p minus p squared, and that's p into 1 minus p, which is q. That's the standard deviation for each one of these xi's. And now let me define this new quantity which I'm going to call Zn. Zn is this Sn here minus n times the mean value of Sn, and we divide it by this. Sigma x, which is pq square root, times square root of n. So that's a definition of this quantity Zn. If I like, I can divide both the numerator and the denominator by n, in which case I'll get this Sn divided by n minus mu x, and here I get the square root of n in the denominator instead of up over here. So Zn is a random variable, and it measures the deviation from the average or the mean n times mu x. What we've shown in the previous calculation is that when you express the result for the probability, then that translates into this. The probability that Zn is between b and a, and these are any real numbers, well, that's this integral. So the binomial distribution goes over into this integral over here, this normal distribution, in the limit where the number of tosses or the number of trials goes to infinity. In the next lecture, I'm going to prove to you a theorem that says that this result over here holds true even if it's not the binomial distribution, it's some other distribution. And that's going to be a very, very powerful result. However, the important thing is that for the binomial distribution, I've shown that this is true. We had to do a little bit of work, but it was very well worth it. Next, we come to the law of large numbers, one of the most famous theorems of probability theory, one that gives meaning to probability itself. So, suppose that x1, x2 up till xn are independent, identically distributed random variables, and again we define Sn as before as the sum of the x's. Each of these x's has the same mean, which we call mu. The law of large numbers says that 1 over n times Sn, that is to say the average value of Sn, takes the value mu with unit probability. That is to say, certainly takes the value mu in the limit that n becomes large. As an example, we take the random variable xi, which is 1 if the ith tosses a head, 0 if the ith tosses a tail. Let's take this unusual probability that the head has probability 2/3, tail has probability 1/3, a bias coin, obviously. Then the binomial distribution tells us that the probability of getting k heads after throwing the coin n times is equal to this: p to the power k, 1 minus p to the n minus k, times this binomial coefficient n choose k. If we make a plot, well, that's the histogram, and this is the curve that approximates that histogram. So this simply is a reiteration of what we've learned. Here the average value of mu is p, and the standard deviation is 1 over square root of npq. Well, there wasn't any surprise over there, but now let's take a second example. Let's choose a number randomly between 1 and 3 and repeat this n times. When I say randomly between 1 and 3, what I actually mean is distributed uniformly between 1 and 3. So the probability distribution is p of x equal to 1/2 inside this interval and 0 outside. So suppose that I take the average value of xi, any one of these random variables. Well, that's half. That comes from the probability distribution. And then x weighted by half, which I've taken outside, between 1 and 3. So obviously that value is 2. If I want the average value of the random variable squared, well then I simply have, instead of x squared here, and that's 13 over 3, which means that the standard deviation is 13 over 3 minus 2 squared, that's 4, and that's equal to 1 over 3. So Sn divided by n, which is the average value of xi, is equal to 2. This is what the law of large numbers is telling us will be the average value of Sn divided by n. And let's look at the average value of Sn squared divided by n squared. Well, that's equal to this, 1 over n squared into all of this. Now, if you look at this, then you notice that x1, x2, etc., because they are independent variables, therefore the average value of x1, x2, that's equal to average value of x1 into x2. And how many pairs are these? N squared minus n pairs. Minus n because the number of such things, x1 squared plus x2 squared plus xn squared, that's a total of n, whereas the total number of terms is n squared. So the number of terms where these two indices are not the same will be n squared minus n. So therefore, if you take the standard deviation here, that's Sn squared over n squared minus the average value of Sn squared, also divided by n squared, that's equal to this. Obviously, that's because there are n such terms and n into n minus 1 such terms, like these. And so this is equal to simply this thing over here, which you recognize as the standard deviation of the ith random variable squared divided by n. And now this sigma squared, as n goes to infinity, will go to 0. So in other words, the fact that sigma squared goes to 0 means that it will become more and more certain that Sn over n will converge to 2. This is summarized over here, that mu will become 2 and sigma will become 0 in the limit that n becomes larger and larger and goes to infinity. But have we really proved this? Although we are close, for a proper proof we will need to do a little more work. Earlier in this course I had mentioned the Chebyshev rule, but I had not proved it. Now that we're doing a proper mathematical proof, we will need to prove it. So, let m be any positive number bigger than 1. So m could be 1.001, or m could be 1.3, or m could be 5.9. It's got to be positive, it's got to be bigger than 1. Here is an obvious statement. So, let's ask what is the probability that the random variable x differs from its mean value, mu, by an amount that is greater than m sigma. So, that means instead of summing over all values of x, we should sum over only those values of x such that the absolute value of x minus mu is bigger than or equal to m sigma. What that means is that x lies between mu plus m sigma and mu minus m sigma. On the other hand, we have defined the standard deviation squared, or the variance, as being the sum over all x. And this is x minus mu squared weighted by p of x. That's just the definition of the variance. Now suppose in this quantity I restrict the range of x. It's the same quantity that I'm summing over. It's x minus mu squared p of x, and of course this is positive and this is positive, so this whole quantity here is positive. But since I am summing over a restricted range of x, therefore this is going to be greater than or equal to this quantity here. This is simply saying that I'm adding fewer positive numbers together, and therefore I'm going to get a smaller sum. The next step is to realize that this x minus mu squared is always going to be bigger than or equal to m squared into sigma squared, because that's the condition that we've put on the range of x. This leads us to the next inequality. So instead of this, I'm going to put this m squared sigma squared, and of course, for the reason I just told you, there's a greater than or equal to over here. Well, this m squared sigma squared does not depend upon x, and so we can just pull it out. But this quantity over here, this is exactly the probability that x will differ from its mean value by an amount greater than or equal to m sigma. And so we have shown that this is equal to m squared sigma squared times this probability. Now all we need to do is divide this side by m squared sigma squared and this side by m squared sigma squared, and so we have a relationship that the probability, this probability, is going to be less than or equal to 1 over m squared. And again, I remind you that m is any number which is positive and bigger than 1. So this is really Chebyshev's rule. We can write it in a slightly different way because this probability is equal to 1 minus the probability of this quantity here being less than m sigma. That's obvious because all probabilities have to sum up to 1, And so therefore there's an equivalent way of writing this, which is here. The probability that x minus mu is less than or equal to m sigma is going to be 1 minus 1 over m squared. This or this are both statements of the Chebyshev rule. So now we're in a position to prove the law of large numbers. Let's begin by defining Sn as being the sum of all the x's from 1 up till n. Remember that these are independent, identically distributed random variables. They all have the same mean, which is mu, and of course the same standard deviation as well. It's therefore obvious that if I take the average value of Sn, well, that's mu plus mu plus mu, n mu's, and so if I divide that by n, like over here, I'll get mu. And so we have the average of Sn over n equal to mu. Let's do this for Sn squared as well. In that case, we have x1 squared plus x2 squared, etc., all the way up till xn squared. And so there are n of these squares. Then we have the cross terms. So then we'll have 2 into x1, x2 plus 2 into x1, x3 plus etc. plus 2 into x1, xn. There'll be an n at this point over here. And then we'll have x2, x3, x2, x4, etc. You can see that there are a total of n squared terms over here, of which there are n terms which have the squares only. So x1 squared, x2 squared plus xn squared, that's n of them. And so therefore the number of cross terms like this amount to n squared minus n. This is the number of such pairs. In that case, the standard deviation squared, or the variance, is going to be the average of Sn squared, divided by n squared, of course, minus the average of Sn squared, divided by n squared. Now, this over here will be n times the average of each one of these, here, 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 and then because there are n into n minus 1 such pairs, well, what's the average of x1, x2? It's just the average of the random variable x1 times the average of the random variable x2. That's because they're independent random variables. And so we'll have n into n minus 1 times the average of each one of them, that is mu into mu. And of course, we divide by n squared. From this, we'll subtract this, which is mu squared. And so simplifying this gives us the average of xi squared minus mu squared divided by n, which, of course, is sigma squared over n, where sigma squared is the standard deviation squared for each random variable, and they're all the same, so there's no need to have an I over here. At this point, we're going to need the Chebyshev rule, which, as we've just derived, tells us that the probability that x minus mu is less than or equal to this is greater than or equal to 1 minus 1 over m squared, where m squared is free for us to choose. So now, since we've calculated sigma x above, that's over here, sigma x is equal to sigma divided by square root n. Therefore, we're going to use this over here. And that then tells us that this probability is greater than or equal to 1 minus 1 over m squared. And so far, we haven't made a choice of what m is, but now we're going to do that. We're going to define epsilon as being m sigma divided by square root of n. That is to say, this thing over here. At this point, the only thing that we can say about epsilon is that this is going to be a positive number because m is positive, sigma is positive, so is the square root of n positive. And now we can substitute this definition of epsilon, put it in over here, and we get this relationship that the probability that x minus mu, absolute value of course, is less than or equal to epsilon has to be greater than or equal to this, 1 minus sigma squared over n epsilon. Now epsilon, like m, is for us to choose, and we're going to take epsilon to be some fixed small number. That number, of course, is independent of n, and now we're going to let n become bigger and bigger, in which case this is going to become smaller and smaller, and so for any fixed value of epsilon, and here epsilon doesn't have to be small, however we can choose it to be small, in that case this probability is going to tend to 1 when we take n going to infinity. So in other words, we have shown what we wanted to, that if you take a large number of random variables and you take their average, then that average will tend to the mean value mu. This is the proof of the law of large numbers. Now this relationship is actually a very powerful one. So suppose we choose epsilon equal to, let's say, 0.01, then it tells us that the probability that x minus mu is less than 0.01 is always going to be greater than this thing over here. And so this relationship over here tells us how big a value of n one must choose in order for this to hold for a given epsilon.